All right, folks. All right, folks. So we are about to measure the force here acting on the sphere, okay, at one distance. And that distance is r squared. That's going to be 8 centimeters. So we're going to make a prediction. All right. We're going to take Coulomb's constant, divide it by 8 centimeters squared. All right. And then we're going to find the slope of the force to the charge square and see how they compare. Okay, we're going to use, and I'm going to show you what we're going to use. I'm going to use 2 different data sets. Let's do that. Go ahead and stop this and let me start sharing. Here. And what I want to do is not look at this one, this stuff here. And I want to go to this particular one. So you'll see that we have voltage points here. Just gonna go ahead and close that. Hopefully everything will still remain open. And with this, we have our 6,000 volts, 5,000 volts, 4,000, 3,000, 2,000, 1,000. All right. So we're going to analyze this data. But I think that it's important before we do that to make sure that our formal specification is here, which is voltage. I left this off. Please forgive me. Let's go ahead and wrap the text here and then middle and center it. I can just double click, or I can make this a little bit bigger and we can see what we have here. You don't have to do that. That's just some formatting that I'm doing. The first thing that I think that I should do, I'm just going to go ahead and find the averages of these. Once I find the averages of them, that's all I'm really doing. I want to have voltage and wire twist right next to one another, and then we're going to analyze it after we make our prediction. Okay. Or before. We'll see how I'm thinking. Okay. So this is going to be the voltage. In volts. Yeah. And this is just going to be equal to what we have here. You guys can see that we have that. And I can do the same thing here, equal to 5,000, equal to 4,000, equal to 3,000, equal to 2,000, and equal to 1,000. All right. So that's our voltage. Now I want to find the wire twist angle. So I want to be a little bit more conceptually qualitative here. Qualitative, I think that's it. And I'm just going to say equals to the wire twist angle. And actually, it's not equal to that. It's the average wire twist angle. Okay. It would be the same for your 2 if you were going to do it. And so this is just going to be equal to the average. And I'm going to select my data here. All right, so we have that, and I should be able to do the same thing. I'm going to copy this and paste it. Let's see how that's behaving. It is selecting the appropriate data set, so our power is increasing. I'm just going to go ahead and copy this and paste it. And paste. Nope, I have to copy it. Paste. Oh, paste. Paste. Yes. All right. So we have all of these. Of course, I think I could remove this stuff here, but we have our averages here. I am thinking just to leave it like so until we need to process it more, because now I want to predict what's going to happen. So let's go ahead and say Coulomb's constant here. And we know that Coulomb's constant is measured in newtons, and I'm going to say meters squared. So we use the functionality here, superscript. That's going to be 2. I'll take away that functionality. And then we're going to divide this by Coulomb's squared. Okay. Yes, it's tedious. So what? And then I'm going to go ahead and say superscript, say OK, then say like so. So let me go ahead and extend this a little bit. I want the newtons to, I would like the units to be on a row, on a column by, I mean, like by itself. So Newton times a meter, centimeter squared. Probably could just did shit though. All right, there we go. Newton meter squared over Coulomb squared. So we know that our Coulomb's constant is going to be 8.99 E9. And then the distance of separation, the charged sphere distance of separation from their centers. Say charged sphere. You guys figure out a better way to say it. Sphere. Um, it's going to be in meters. Okay. We know that it's 8 centimeters from the experiment. So that means that this is going to be, and I typically do like to write in the 8 and then do the conversion. But in this case, I can just write 0.8. All right. So it is 8 centimeters. And now let's do our dialectic synthesis or our theoretical prediction. Expected value for the, I'm just going to say slope measure. And now those are in units. Yes, we could say, so if I do charge squared times Coulomb's constant, then is that what I want? Nope, not that. So we're looking at the slope. It's distance squared over, I don't know what it is. Let me see, what is our expected value? So if we do the force, which is a Newton, over the distance squared, it should be force, it should be Newton meter squared. There it is. Newton meter squared. All righty. So it's Newton meter squared. Let's see here. We're going to go ahead and make our prediction. This is going to be equal to Coulomb's constant divided by the power of the sphere squared. The separation distance, not the sphere, but the separation distance squared. So we're expecting 1.40 E plus 12. Okay. So let's go ahead and bring our voltage over. So what's going to be on the y-axis? Force is going to be on the y-axis. All right. So we need to find the force. Well, that's not really necessary right now. Let's just go ahead and bring our voltage over. And we're going to bring our average wire twist angle over so that we can start processing. So this is going to be equal to 6,000, 5,000, 4,000, 3,000, la da da, la da da, 2, and then we are going to have 1,000. So this corresponding angles, our wire twist angles, are going to be as such. Can I just bring that over? I think so. Uh, see, I should be able to select this and then fill to the right. Yeah. And then I should be able to fill down. No, it didn't work. So let me pull this over, go to 4,000. I literally should be able to just do this, pull them all over to the right. So you'll see all of my angles are coming directly in. Beautiful. Now we can start processing things appropriately. So let's first calculate the charge. So we need to know that the sphere radius, okay, and the way it's giving to us is in centimeters. I think it's important. So we have our sphere radius, and then we have the uncertainty in the sphere radius. Okay, so we have an uncertainty. So this is going to be in centimeters. All right, we will convert those. And since I'm bringing in the uncertainty, and I think it's important, I wasn't thinking that way at first. I'm going to go ahead and insert, and we have the uncertainty, the voltage measurement. This is all about repeatability. Can it be repeated? And to what, how certain, and when I say how certain are we, it's just really like, what are your limits? And I think about repeatability. Can someone else repeat this? And then how do you know you've actually repeated it? Yeah, and I believe that that uncertainty is what you need in order to do it. I'm still trying to wrap my brain around it. But so the uncertainty is 1%. If you guys remember, it's going to be equal to this. It's times 1% plus 10. All right. So that's the uncertainty for that one. Bring these down. So we have our uncertainties here. Okay. Um, so the sphere is 1.9000, and the uncertainty, and I do want to, that's how it's given to us. This is going to be 0.025. All right. So do I need to pull those down? No. And so I'm going to go ahead and convert these. So I want to convert these to meters. I'm just going to drag this over. All right. All right. So in our conversion, of course, we're going to do convert. And I'll just select this, comma, centimeters, comma, meter. All right. And I want to do the same thing here. All right.